Okay, so anyway, let's start our second lecture. And actually, the way I did, typically I will give you a brief overview to highlight the key point of what we discussed last time. So at least you have an idea of those key thoughts. And also you can see, hopefully you can see a clear connection from dot to dot. Like what we discussed in the last week, basically we start the concept of the so-called electrical field, right? And again, everything starts from electrical charge. When it comes to the discussion of electricity, everything starts from electrical charge. So that is why here, first of all, we need to understand the basic property of electrical charge. And here the basic property, first, the charge type, or the so-called charge polarity, can only be positive or negative. And the second property is the so-called charge conservation, meaning the amount of the charge, the total amount of the charge carried by any kind of object. If it's considered as, let's say, a closed system, the total amount of charge is always conserved, meaning it's fixed. What is happening is just there will be charge transfer from one object to another object, but overall the total is still the same. The second property. And the third property is the so-called charge quantization. So basically it means the exact amount of charge carried by any object can only be the so-called quantized number, which equals to this capital N times this E. And this capital N is just an integer number, can be positive, can be negative. Well, this E is the charge carried by one electron. And this is the so-called charge quantization. The three most basic property of electrical charge. And the second point, based on how those electrical charge can move in different material, we can have conductor, we can also have insulator, and in between is the so-called semiconductor. And here the so-called conductor is just some kind of material in which the electrical charge can move freely. While on the other hand, if we are talking about insulator, basically means the charge is fixed in the material, spatially fixed. It cannot move from one point to another point. This is the difference between insulator and conductor. Right? And of course, semiconductor means it's something in between. But most of the time, the situation we are going to handle is just insulator or conductor. Right? And the next point is the so-called electrical force. And electrical force, this is the very first formula in the second part, how we can quantify the electrical force F between 2 point charge Q1, Q2. So again, here you can see for this formula to be valid, the requirement is that this Q1 and Q2 can be considered, both of them can be considered as point charge. And there are two scenarios where you can consider them to be point charge. The first scenario, if both the Q1 and Q2, the size is very small or negligible, then that is the most basic scenario. Both can be considered as point charge. Or another case, more realistically, if the size of Q1 and Q2 are much smaller than this distance r, then effectively we can still consider both of them to be point charge, meaning this formula is valid. Right? So here you can see basically you need this three parameters in order to quantify the force between two charges, Q1, Q2, and the distance r. Right? And this is the case for two charge. And if you have multiple charge, the way you do it is to apply the so-called principle of superposition. Basically, you find out the vector sum of multiple electrical force. That is going to give you the total electrical force. And the next one is basically the most important part, the electrical field. And the electrical field typically will write down with this capital E, vector E, and this is a relation between F and E, F and E. So here you can see this E, this electrical field is actually just can be generated by one charge. It's kind of intrinsic property of a charge. While this F is the interaction between at least two charges. So that's why here you have this additional E in order to convert from E to F or from F to E. Right? And similarly, if you have multiple charge, the total E, you apply the principle of superposition to find out this total E field due to multiple charge Q. Right? So this is a case for single point charge. And in reality, of course, you may not always have a single point charge. You may have multiple charge, or you may simply have infinite number of charge. And the most common scenario you will need to deal with is the so-called continuous charge distribution. So continuous charge distribution basically means you have certain kind of charge object, and the charge is uniformly distributed in the entire object. So this is the so-called continuous and most of the time uniform charge distribution. And if this is the case, if we need to figure out this, let's say this is capital Q, we need to find out this, let's say at this point, the electrical field E at this point due to this capital Q. And the way we do it, because now this total capital Q is not a single point charge anymore. So the way we do it is first we purposely create or identify an artificial point charge, dq. And the way we define the dq is like this. Simply, we define a tiny portion, let's say a tiny portion within the total object. And let's say if it is a three-dimensional object, then the charge density times the volume of the tiny portion basically is the total charge carried by this tiny portion, right? Density, charge density times volume is the total charge, right? And as long as this dV is small enough, then we can consider this to be a point charge. And once this dq can be considered as a point charge, then we can apply this formula to determine this dE due to dq. Again, remember, this is valid only for single point charge. Now we purposely create a single point charge dq. So that's why this is valid. And from this dE to this total E, what we need to do is to do this mathematical integration over the entire object. And what you get is the total E at this point due to this capital Q. So this is the idea or the logic how we can determine the total electrical field if the total charge is not a single point charge anymore. And actually, later you will find out we will do this kind of process. Let's say if we label this as step 1, step 2, step 3, we will do this actually multiple times for different parameter. Now we are doing this for electrical field E. Later we will do something similar for other parameter as well. So it's important for you to understand the logic from step 1, step 2, and step 3. And one last point we briefly covered is the so-called electrical field line. And the electrical field line is nothing but some artificial lines which we used to visualize the electrical field E. It helps us to visualize the distribution of electrical field E in real space. So in order to serve this purpose, basically those electrical field lines need to reflect the magnitude and also direction of electrical field E at any point, right? And in order to do this, there are some so-called rules in order to draw the electrical field line properly. Like the first one, at any point, E is tangential to the electrical field line, and it always starts from positive charge to negative charge, and there can never be two electrical field lines close each other. And finally, the density of electrical field line should reflect the magnitude of electrical field E. So meaning if you have more electrical field line within given area, basically means the electrical field E, the intensity or the magnitude is higher in that area. Right. And of course, some typical electrical field line of some typical charge distribution, like here, positive, negative, positive, positive. Right. A very typical electrical field line, you should be able to at least understand the meaning of the electrical field lines. Like let's say in this case, here you have two charges, a blue one, a green one. So based on this given electrical field line, can you tell me, first of all, the charge polarity of these two charges? Let's say the blue one, positive, negative. The green one, positive or negative. First of all, charge polarity. The blue one should be positive, right? Simply, it always starts from positive charge and entering the negative charge. So then this green one should be negative. This is positive, negative. This is the polarity. Then how about the amount of the charge? The amount of the charge carried by this blue and green one, is it the same? Or if not, which one is larger? Which one is larger? Yes, the positive one, this blue one, the amount of the charge should be larger than the charge carried by this one. And the so-called reference basically is this scenario. If you have two positive and negative charge of the same amount, then this is the electrical field line. Now you can see, of course, basically this, let's say the so-called, this area is pretty much similar to this case, right? But if you look at this area, you can see all those electrical field line looks more like the electrical field line of positive charge instead of negative charge, right? They are still leaving the charge instead of going into. Meaning, even at this site, the effect of this positive charge is still stronger. So in order to have this stronger effect, basically means charge Q carried by this should be larger. Right? This is how you can not quantify but qualitatively tell the charge distribution based on the given electrical field lines. Right. So those are the key points we discussed last time. So here you can see we start from electrical charge, and then we can define the electrical force and electrical field for a single point charge, and move on. We can do the same, define the electrical field and also electrical force for this kind of continuous charge distribution, right? And as this is the last slide for the last week's lecture. So you can see the question is, how are we going to determine the electrical field E in some other case? Like in the first case, if the charge is not uniformly distributed, or in another case, if it is uniform distributed but is an infinite large charge object. So how are we going to do this? Of course, in principle, this step 1, 2, 3 are still valid. Physically, they are still valid. It's just eventually this integration, you cannot solve it either because it's non-uniform or because it's infinitely large. So you cannot do this integration directly. So that is why we need to come to the Gauss's law, the key part of today's lecture, how we can use Gauss's law to determine the electrical field E for this kind of scenario. So here, first of all, when it comes to Gauss's law, the very first application is to determine the electrical field E. Right? So that is to say, another way to say, when it comes to, let's say, some question asks you to determine electrical field E, maybe the first reaction, your first reaction is to see if Gauss's law can be used. And in order to establish this Gauss's law, we will need to, first of all, introduce some new parameter and also concept. The first one is the electrical flux. And the electrical flux is a physical parameter, basically measure the number of electrical field lines. The number of electrical field lines penetrating through a surface. So now you can see this electrical field line, the very last topics we covered in the first lecture. Now you see the connection between the electrical field line and this new parameter electrical flux, phi E. Right? So it measures the number of electrical field line penetrating through a given surface. And if we write down this definition into a formula, basically is this, right? This is the definition of electrical field or electrical flux. This E is basically the number of electrical field line times the area, so that is the total number of electrical field line, right? So that is why we can write down, define this kind of parameter as electrical flux. Right? And of course, this is a very basic scenario. In some case, the electrical field line may not penetrating through the surface perpendicularly, meaning there may be an angle not 90 degrees between them. So in a more general way, this is how we define the electrical flux for any surface. For any surface, the electrical flux equals to the dot product of E dot A, vector E, and vector A, the dot product of these two vectors. And of course, the first term is just the electrical field E as a vector, meaning you need to consider both magnitude and direction of E. While for the second vector, this vector A, in terms of the magnitude, is just the geometric area of a surface. Like for this kind of rectangular, then the area, the magnitude of this vector A is just, let's say here is A, here is B, is just A times B. This is the magnitude of the vector A. While for this direction of this vector A this is the way we define it. It has to follow the surface normal. The surface normal gives you the direction of the vector A, right? And this, again, this is just convention. There is no physical reason why this A is defined in this way. So now you can see this general form of electrical flux, vector E dot vector A. Right? So here you can see actually in order to apply this formula correctly, I would say the most important step is to figure out the direction of vector A, because the others should be quite straightforward, whether it is the E or it is the area of the surface. Right? So you need to define this direction of the vector A properly. Of course, if you look at this kind of surface, this purple surface, actually you can tell the so-called surface normal can be this direction, can also be this direction, right? Surface normal up, there's also surface normal down, right? If we are talking about this kind of open surface, both definitions are valid. Both definitions are valid, meaning you can define the direction of vector A either in this direction or this direction. Both are correct. But for us, actually, most of the time, the surface we need to deal with is a closed surface. Closed surface like this kind of cubic or a sphere. This is the so-called closed surface. And when it comes to a closed surface, of course, this general formula is still valid. And the E, electrical field E, magnitude, direction, still the same. And the vector A, the magnitude is still the geometric surface area. But now the direction of this vector A, there's only one way to define it. It must to be along the surface normal and at the same time pointing out of the surface. Pointing out of the surface, pointing away from the surface. Like if we are looking at, let's say if we are looking at this surface, so it's part of a closed surface. The entire cubic can be considered as a closed surface, right? So let's say if we are looking at this one, of course, this is a E, it's constant. Then for this surface, you can only define A in this way, in this direction. You cannot define in this direction. This is wrong. So this is the so-called pointing out of the closed surface. So pay attention to the difference. If it is an open surface, you have two options to define the vector A. If it is a closed surface, you have only one option. And again, most of the time for us, the case we deal with is closed surface, meaning this kind of definition actually is more relevant for us. Right? And from this definition, of course, then we can tell for some surface, although this phi e itself, the flux itself, is not a vector, is a scalar, but it can be positive, it can be negative. Here, the positive, negative is just the physical meaning. The flux can be flow into the surface, can also be flow out of the surface. And we define flow out of the surface to be positive and flow into the surface to be negative. Right. So this is how we can generally determine the electrical flux for the closed surface. So again, you can see the most important thing is to define the vector A, to define the, or more accurately speaking, to define the direction of vector A. Right. And of course, this one, the simple formula is valid. If you want to use this formula directly to determine, to calculate this phi E, then that means both E and A should be uniform, right? If not, if one of them is not uniform, then you cannot use it directly. And the so-called uniform, of course, uniform E is straightforward, the constant electrical field E. Well, this uniform vector A, it basically means it's a flat surface. Because for a flat surface, then on the entire surface, the A is the same. The vector A is the same. If it's a curved surface, like the curved surface, then the A at this point, they are different. And then you cannot consider it to be a uniform A. Right? And again, if either of them is not uniform, and the general approach how we can determine the total flux is like this. It's like this. If it's a finite number of surfaces, then you just do this for each surface, each flat surface, and add them together, you will get this total flux. If what you have is infinite number of flat surface, like this kind of curved surface, then what you need to do is to do this integration along the entire surface. So you can see pretty much the similar idea like here, right? If one of them is not uniform, then basically you create a tiny surface dA. As long as this dA is small enough, then for sure the electrical field E within dA must be uniform. So that is to say, let's say you create this kind of infinite small surface dA, then for this surface, both E and A must be uniform. And then you can use this formula directly to find out the flux for this tiny surface. And you do this integration along the entire surface. Entire surface means this surface. And by right, what you get, it should be the total flux, right? And of course, the exact type of integration will depend on what kind of surface you have. So this is the electrical flux. So basically now in principle, we can determine the electrical flux for any surface, right? So let's say if you look at this example, ask you to determine the electrical flux through a sphere of radius of 1 meter, and it carries a charge of 1 microcoulomb at the center. So here, this is a charge, and ask you to determine the flux electrical flux through this surface, this sphere. Again, here is not a circle, but instead it's a sphere surface, right? So, right, first of all, you need to tell me whether you can use this formula directly to get the flux for this case. Can you use it directly? And whether you can or cannot all depends on if both of them are uniform. Let's say if we look at this surface, this is the first surface we are looking at. This is the charge. If we look at, let's say, this point 1, here we have point 2. First of all, can you tell me the vector E at point 1 and point 2, are they uniform? Then how about A, vector A? Are they uniform? Again, for this A, let's say we define a tiny surface. We define a tiny surface here and tiny surface here. Assume the area of this surface is the same. How about the direction of these two surfaces? Are they the same? No, right? Means actually both E and A are not uniform. And of course the same, the 0.3, 4, 5, basically on any point on this Gaussian, on this spherical surface, both E and A, vector E and vector A, are not uniform. If both of them are not uniform, of course, you cannot apply this directly to get the total flux. And if this is the case, what we need to do is, first of all, create a tiny surface, let's say like this kind of tiny surface, and assuming the surface area is dA. Surface area is dA, and if we can find out this electrical field E at within this surface area, then the dot product will give us the flux through this tiny surface. We continue to do this integration. That should be the total flux, right? So again, this is, I would say, one of the most important steps you need to be able to understand, not only to kind of copy, right? Why this is the case, why this is valid. Right? So now, of course, here, this E is due to this single point charge Q, right? This E is all due to this single point charge Q. And for electrical field E due to a single point charge Q, we have this formula, right? We have this formula. And if we look at this two vector E and vector dA, let's say, again, if we come back to this tiny surface, first of all, this should be the direction of E, right? Because here you have positive charge. So positive charge, this is going to be the direction of E field. Then how about this direction of dA? Direction of dA, again, this now is a closed surface. So the dA should be pointing along surface normal and at the same time pointing out of the surface. So for the dA, this should be the direction, right? Meaning actually this vector E and vector dA are parallel. So that is why you can just write down in this way, E dA, of course, actually there is a cosine 0. This is so the solution of the dot product, right? the dot product of two vectors, EA times cosine theta. Now, in this case, E and dA are parallel, means there's a cosine 0, which is 1. So that is why here from this term to this term. You see the difference? Here you have two vectors. Here it's become just two scalar. Simply because at any point on the surface, E and dA are parallel. So that is why this one, the vector dot product is always equals to this E times dA. Right? And again, now if we only consider the magnitude, the E should be constant. It's just the direction is keep changing. But if here we only consider the magnitude, E is constant because you can see here it's constant. So what you need to do actually is just the integration of dA. And integration of dA along this entire sphere basically is the surface area of the sphere with radius r. Right? This is the surface area of a sphere with radius r, 4 pi r squared. Right? So then you can see this one, the r squared cancel. What you have is this Ke times 4 pi. You can write down in terms of this 1 over epsilon naught is another constant. Right? So you can see it just equals this Q times this constant. So here I try to go through the details because similar idea how we can simplify this kind of integration based on some symmetric consideration. This is some similar analysis we are going to again repeat quite often. Basically, you need to understand step 1 and step 2, and then from here to here, step 3. You need to understand why this step 1, 2, 3 are equal. So, any questions before we move on? So here again you can see it involves some integration, but actually you don't really need to do any mathematical calculation. All you need to do is to, based on some kind of symmetric argument or symmetric analysis, so you can simplify this integration. So this is this example. So next is what do we really mean by this Gauss's law? So and how we can use the Gauss's law to determine electrical field E. And first of all, the so-called Gauss's law basically tells you the net electrical flux through any closed surface is proportional to the net charge enclosed by the closed surface. Or another way to say it's proportional to the net charge inside the closed surface. And if we put this into a formula, first of all, this net electrical flux through any closed surface is this one, right? This is the electrical flux through any closed surface. And this one is proportional to the net charge inside. So this is another term. So you can see this Q in. This is the total charge inside the closed surface. So this is so-called proportional. Right? Total flux equals to this. Right? So this is the so-called Gauss's law. Right? And if we have the Gauss's law, actually, now we don't really have to do this kind of integration to determine the flux. But instead, let's say if we have this kind of 5 charge, Q1, Q2, Q3, Q4, Q5, and there is a closed surface, this kind of closed surface is kind of arbitrarily closed surface. Again, this is not a loop, but imagine it to be a 3-dimensional closed surface. Then, based on the Gauss's law, we can immediately tell the total flux, total electrical flux through this closed surface, phi E should equals to this. Q in over epsilon naught. And in this case, Q in, you have Q1, Q2, Q3 inside the closed surface. That is why in this case, the Q in is Q1 plus Q2 plus Q3. Right? So you can see, based on the Gauss's law, it becomes very straightforward to determine this phi E. Right? So similarly, if this is the situation, now you have one charge, Q, and different surface. Again, different closed surface, S1, S2, and S3. Immediately, we can tell the electrical flux through surface S1, S2, S3 should all equals to this, Q over epsilon naught, because here the Q in for S1, S2, S3 are the same. Right? Are the same. And again, that if you have this charge Q stay outside of the surface, immediately you can tell the total flux through this surface is 0, because now this Q is outside, is not inside the surface. So this Q in is 0. QE is 0. Right? It's very straightforward. So of course, until now we have 2 ways to determine the electrical field E. And the first one is the formula we introduced in the last lecture. So you do it from point charge dq to electrical field E. This is one way. And another way, you can see just now, basically, based on this Gauss's law, we have another way to determine this E, just based on the Q in, the total charge inside the surface. Right? Of course, there are some so-called difference between these two methods or different laws. First of all, for this Coulomb's law, it's always valid, physically and mathematically always valid. But whether you can use this Coulomb's law to do this, that is another thing. Whether you can find out this final solution, that is another thing. This, the idea is always valid. As long as you can define a single point charge, then you do this integration, that is going to give you the total E. While for this Gauss's law, in order to apply this Gauss's law, first of all, you will need to have a closed surface. A closed surface. So you can see here you have the integration along the entire closed surface. And here you need to consider the closed surface so that you can define this Q in, right? So basically, on the left side and the right side, it always both involve a closed surface. It means this Gauss's law is only valid, physically valid for a closed surface, not any arbitrary surface, right? And this is the first thing. And the second thing, more importantly, in order to use this Gauss's law or use this formula to determine this E, this closed surface cannot be any arbitrary closed surface. It has to be some kind of closed surface with high degree of symmetry. And if you can define this kind of closed surface, then that is what we call the Gaussian surface. Meaning, again, the formula is valid for any closed surface, but you need to have a Gaussian surface in order to use this formula to quantify this E, to mathematically find out the solution. So pay attention to this difference. Open surface, closed surface, Gaussian surface. Right. So of course here we have some the so-called criteria in order to define a Gaussian surface. And here we list the criteria 1, 2, 3, 4. 1, 2, 3, 4. So first of all, it's not saying you need to have a surface to fulfill all the 4 criteria at the same time. You can still have a Gaussian surface. Let's say it may only fulfill 1 of them, 2 of them, 3 of them, or in some cases for all of them. Right? Here is just some optional criteria. Like in the first case, the first one is that the electrical field can be argued to be constant, or the magnitude of the electrical field can be argued by symmetry. Just by symmetry, you don't need to do any calculation. You already know the magnitude of the electrical field is constant over the entire surface. Like in this case, then you can already know, again, by symmetry argument, you can tell the intensity or the magnitude of electrical field at point 1 and point 2 must be the same, right? So this is the meaning of the first point. And the second point, the dot product of E and dA can be expressed as simple algebraic product because they are parallel. This is one scenario where you can simplify the integration, or another scenario if they are perpendicular. And like for the second point, E and dA are parallel. Again, if you look at this case, that is exactly why we can do this step 2, because E and dA are always parallel, right? E and dA are always parallel for any point on this surface. This is the mean. Of course, in some case, they can be perpendicular. Perpendicular means the dot product is cosine 90 degree, is always 0, right? And another case, if E field is 0, of course, then you can also simplify this integration. So of course, here then you can tell, in order to apply this Gauss's law, actually it requires you, the very first step is to construct a Gaussian surface. And in order to do this properly, of course, you will need to have some practice, and eventually, I would say, also require a bit intuition. And of course, intuition comes from practice. But this being said, eventually, we are not going to test you with some very complicated scenario, meaning we are not going to ask you to construct a Gaussian surface, a very complicated Gaussian surface. All the examples we are going to discuss during the lecture, during the tutorial, pretty much is the requirement you need to be able to handle. Okay, so before we have a break, let's quickly look at this example, how exactly we can use this Gauss's law to determine electrical field E. Right? Like in this case, it asks you to calculate this electrical field E at the point outside, inside an insulating sphere of radius A, and it have a uniform volume charge density rho and total charge capital Q. Right? So basically, it asks you to determine the electrical field E at some point, let's say here, outside the sphere, or some point here, inside the sphere. Right? So for the first case, if you look at this at a point outside the sphere, so in order to apply the Gauss's law, again, the first step, you need to have a Gaussian surface. You need to have a Gaussian surface. And in this case, a proper Gaussian surface will just be this kind of sphere, which is concentric to this charge sphere. So this is going to be the Gaussian surface you are going to construct, this one. And once you have the Gaussian surface, then you apply the Gauss's law, which basically tells you the total electrical flux through this Gaussian surface should equal to this Q in over epsilon naught. Right? This one should equal to this Q in divided by this constant, right? So now, first of all, let's look at this Q in. For this Gaussian surface, the Q in should be just this total charge Q, right? Because now the Gaussian surface is outside the metal sphere, right? And this is the first part. And the second part, we also need to figure out this integration, the integration of EDA. And for exactly the same reason we just discussed here, step 2, the step 2. This integration of the dot product will equal to this integration of this EDA. Again, because at any point, vector E and vector dA are parallel. On this point, this point, this point, this point, any point. Right? Again, another step, the magnitude of this E by symmetric argument, it should be constant. Constant means you don't need to do any integration of E. But instead, you only need to do integration of dA. And the integration of dA is just the surface area of this Gaussian sphere. And the Gaussian sphere, the radius is r. So it's 4 pi r squared. And you can find out this electrical field E by using the Gauss's law. So you can see the general approach, general way to apply the Gauss's law to determine E. First of all, of course, you need to write down this one. Step 1. And step 2, you figure out this Q in certain way. And step 3, you find out this integration, the integration of EDA, the mathematical solution. And again, most likely you need to do some kind of simplification instead of directly to do the integration. Right. Step 1, 2, 3, to apply the Cauchy's law to quantify the electrical field E. And the same, if we are talking about a point inside the charged sphere, then first step, you will need to have a Gaussian sphere inside this charged sphere. Right? Let's say now this is going to be a Gaussian sphere. Once you have this Gaussian sphere, you write down this equation. The integration equals to this, right? And the second step, of course, you can either do this integration first, or you can quantify this Q in first. Like in this case, for this integration part, exactly the same reason, it should equals to this. Now it's just this R is inside the charged sphere. Then how about this Q in? Is this still equals to this capital Q? Is this still capital Q, like here? Here the Q in is capital Q. All the charge is inside the Gaussian sphere. But how about here? Now, this is the charge object, and this is the Gaussian sphere. So the Gaussian sphere is inside the charge. That means only part of this capital Q is inside the Gaussian surface, right? Not all the capital Q. So how can we determine this Q in? So because here it tells you the charge density, and also the charge is uniformly distributed. So then this Q in should equals to this charge density times the volume of this Gaussian sphere. This should give you the total charge inside the Gaussian sphere, right? Again, density times the volume. And you can find out this E, electrical field E, in this way in terms of the density and the radius. And of course, you can also write down this density in terms of the total charge, capital Q. Right? So this is how we can, again, determine the electrical field E specifically based on the Gauss's law. I think we have one more example. Actually, once you understand the general logic, actually, this case can be quite similar. It asks you to determine the electrical field E due to a non-conducting insulator, an infinite plane of positive charge with a uniform charge density of sigma. Right? So again, the very first thing you need to do is to construct a Gaussian surface. And in this case, a proper Gaussian surface, actually, it should be this kind of Gaussian cylinder. And again, why this Gaussian cylinder is a proper Gaussian surface? You will need to do some practice, and later you can have this kind of intuition to construct a proper Gaussian surface. Like in this case, the so-called Gaussian cylinder basically is a cylinder. Part of the cylinder is above this charge plate. The solid line, this portion is above this charge plate, and the dashed line region this region actually is below the charge plate. So basically, this Gaussian cylinder penetrating through the charge plate. And once we have the Gaussian surface, then we can apply the Gauss's law. The total electrical flux should equal this Q in, right? The first step, this one equals this one. Of course, here everything is right in this way, but when you are not familiar enough, you can just write down as step 1, 2, 3. The step 1 is just this phi E equals to this. And then the step 2, for this, let's say for this Q in, the total charge inside this Gaussian cylinder is only contributed by this area. It's only contributed by this area, right? And again, here we consider this charge plate as a two-dimensional object. So the total charge within this area should be equals this two-dimensional charge density times two-dimensional area will give you the total charge inside the cylinder, right? So this is step 2. And then step 3, for this integration, how we can do the integration to get this total flux, we will need to do a bit symmetric analysis. So first of all, if we consider this kind of Gaussian cylinder, so basically you can consider it, let's say, as 3 surfaces, top one, bottom one, and there is also a curved surface, right? And now this Gaussian cylinder is penetrating through the charge plate. Basically, the charge plate is somewhere here, right? Then, for the curved surface, for this curved surface, we can tell any point on the curved surface, this should be the E. This should be the E, right? And this should be the dA, meaning on any point on the curved surface, E and dA are perpendicular. The dot product is going to be 0. Or another way to say, the curved surface, the total flux through the curved surface is 0. So all you need to figure out is the flux through the top surface and the bottom surface. And again, by symmetric argument, we can tell the magnitude of the flux should be the same, because E and A are the same for both surfaces. So that is why all you need to do is to do this integration for 2 flat surfaces. And this 2 flat surfaces should be the same. So it's 2, a factor of 2, and you do integration for 1 surface. Right? And again, if we look at this 1 surface, let's say for the top surface, this is still going to be the E. And A should also be this direction. If you look at the bottom surface, then this is the E. This is also the A. Meaning, for both surfaces, E and dA are always parallel. So all you need to do is just this E times A. E times A. So that is why how you can move from here to here. And again, for all the process, you are not really doing any mathematical calculation. It's just by having some symmetric argument or discussion. Right? And immediately, you can get this E, electrical field E, due to this kind of infinite charge plate. Right? So, okay, I guess that is all for the 2 examples. to show you in detail exactly how we apply the Gauss's law to determine the electrical field E. So, okay, let's have a 10 minutes break, then we come back to continue the next topic. Okay? Okay, so let's continue. For the Gauss's law, in addition to give us a quite straightforward way to determine the electrical field E, actually there is some kind of understanding we can derive based on the Gauss's law for some conductors. And here the so-called conductor we are talking about generally is a conductor in the so-called electrostatic equilibrium condition. And the meaning of this electrostatic equilibrium condition is just means for this kind of conductor, there is no net charge motion on it. Then of course, if you look at the single charge, it's still going to move freely because anyway it's a conductor. But overall speaking, there is no net charge movement, meaning you have charge move in this way, at the same time there's a charge move in this way, opposite way. This is a so-called no net charge motion. And once the conductor is in this kind of condition, there are four properties we will discuss one by one. And the first one is the electrical field E. So basically E is always zero inside the conductor. Meaning, let's say if let's say this is a conductor and it tells you this conductor is in electrostatic equilibrium condition, immediately you can tell E at this point, this point, this point, this point, this point, any point inside the conductor is zero. And the reason for this is like this. The analysis to derive this understanding or to derive this property is this, because if we assume E is non-zero, let's say there is a finite electrical field E, there is a finite electrical field E inside this conductor. So what will happen? What will happen? Because we say the conductor, of course, inside there is a lot of, let's say, a lot of electron. There is still a lot of electron, right? And if at the same time you have a finite electrical field E, then of course there will be an electrical force for those electrons. Electrical force, Fe, right? And if there is a net force on those electrons, then they're going to move, all of them going to move in the same direction, right? If all of the electrons encounter an electrical force of the same direction, then all of them is going to move along the same direction. Then it's not the so-called no net charge motion. Meaning, if you have finite E, then there will be a net motion of charge. Then, in the opposite way, if there is already no net charge motion, this E must be zero. E inside the conductor must be zero. So this is how we derive the first understanding. Electrical field E inside the conductor must always be zero. And the second property is if the conductor carries any amount of the charge, then all those electrical charge can only stay on the surface. So any excess charge on an isolated conductor must reside entirely on the surface. So how do we understand this? Like, if we look at this kind of conductor, based on the first property, we already know inside the conductor, anywhere inside the conductor, E is zero, right? And if we construct this kind of closed surface or Gaussian surface just close to the surface, but inside the conductor, like this way, like this kind of Gaussian surface. Then for this Gaussian surface, we can have the Gauss's law, which tells you the total flux should equals to this, and also equals to this Q in, right? And this will always be 0. Why? This will always be 0. Why? Even you have no idea about this Q in, still you can tell this should be 0, must be 0. Because E is 0. Then, of course, this dot product is always going to be 0. This integration is always going to be 0. Right? And if this integration is always to be 0, means this Q in must always be 0. Whatever Gaussian surface you have, as long as it is inside the conductor, then this Q in must be 0. And if this is the case, that means the charge inside the conductor is always 0. But if at the same time this conductor do carry certain amount of the charge, then it can only stay on the surface. Right? It can only stay on the surface. This is the second property. So the first one, inside E is 0. The second, inside Q is 0. And the third property is about the magnitude of the electrical field. So it tells you the electrical field outside a charged conductor is given by this term. So sigma over epsilon naught. And this sigma is the surface charge density. The surface charge density. Let's say at this point, you will have this E1 equals this sigma 1 over this constant. Well, on another point, E2 equals to sigma 2 over this constant. And E1 and E2 may not be the same because this sigma 1 and sigma 2 may not be the same. Right? So how this one is derived? How to derive this one? So of course, what we need to do is to apply the Gauss's law. Apply the Gauss's law. Let's say you have this kind of surface, and you construct a Gaussian cylinder, and then you can apply the Gauss's law for this Gaussian cylinder. You can find out this E. So now, pay attention to this one and this one. You see the difference? It looks like quite similar. You have this kind of two-dimensional charge distribution, and you have this kind of Gaussian cylinder. But you see the difference? Here you have a factor of 2, right? And here you don't have. Basically, it tells you the E field here, due to this kind of conductor, is twice of the E field due to this charge plate. Right? So why this is the case? Why this is the case? Sorry? It is closed surface, yes. And so what happens inside this so-called closed surface or the conductor? Yeah, E is 0. So you can see, basically, if we come back to this detailed step, here you have two flat surfaces to give you the finite flux. top surface and bottom surface. But here, you only have this surface, the so-called top surface. While this bottom surface, it is inside the conductor, E is 0, then flux for this bottom surface is going to be 0. So that is why here you have this E to be twice of the electrical field E for a two-dimensional charge plate. So other than this, again, the detailed step, the reason, underlying reason is exactly the same. Why this integration is just equals to this. This is the third property. And the fourth property, so basically it's another version of the third one. So you can see here the E is a function of sigma. E is a function of the surface charge density. And in reality, this surface charge density is going to depend on the geometry of your conductor. And what will happen is the larger curvature for a given conductor, a larger curvature means the surface charge density is larger. Like if you look at this kind of object, the so-called curvature, basically here at this point, this curvature is larger than the curvature at this point. 1, 2, 3. The curvature of point 1 is larger than the curvature of point 2 and larger than the curvature of point 3 because here 3 basically is flat and in terms of curvature it's 0. Right? So then you can tell this sigma 1 larger than sigma 2 larger than sigma 3 and accordingly E1 larger than E2 larger than E3. So these are the four properties of a conductor we can derive based on the Gauss's law. And of course here the case we have discussed is so-called the simple scenario where you just have one isolated conductor. If inside the conductor, let's say you can have this kind of so-called cavity, basically is an empty area, and also depending on the situation inside the cavity, whether you have charge inside the cavity or another case you have a finite charge inside the cavity, then the charge distribution and electrical field E for this conductor is going to be different. And for this part, basically this slide, this one, I leave it to yourself. Try to see if you can understand all those these three slides and the relevant scenarios. Right. And of course, the analysis is pretty much the same as we did here. Okay, one more example. So here asks you to calculate the electrical field E at a point A outside and inside a thin spherical sphere of radius A and also have total charge Q. So now in this kind of charge object, it's a thin spherical sphere and the radius is A. Similarly, ask you to determine the E field at this point or at this point, right? Outside and inside. So the same, in order to apply the Gauss's law, first you will need to construct a Gaussian surface. And in this case, it should also be this kind of Gaussian sphere. The Gaussian sphere outside outside this spherical shell, right? And you can apply the Gauss's law, the flux, basically the flux E equals to this, right? The integration, and also E equals to this Q in divided by the constant. And if this is a Gaussian surface, then the Q in is just capital Q, right? And again, from here to here, the same reason, the same analysis, the same reason you can find out is just E equals to this E times 4 pi r squared. So you can find out E outside this spherical shell, and if it is inside, let's say somewhere here, then you will have a Gaussian surface, like here, a Gaussian surface inside the spherical shell. And if you apply the Gauss's law, integration E equals to Q in over epsilon naught. Now, Q in is just 0, right? Because you can see charge is here, is on this spherical shell, and this is your Gaussian surface. Then, of course, for the Gaussian surface, the charge inside is just 0. And immediately you can tell, of course, E must be 0. E must be 0. So this is another example of how we can apply the Gauss's law to determine the electrical field E. Okay, so this is all for the electrical field. And next, we will move on to introduce another parameter and, of course, relevant concept, relevant formula for the electricity. And that is the so-called electrical potential or potential energy. So basically, this electrical potential is a parameter that describes electricity in terms of its energy. In terms of its energy. The energy associated with the electricity. Like, of course, this is quite general concept for any field. For the electrical field, we have electrical potential. There is electrical potential energy. For other field, like the most common one, the gravitational field, there is also a gravitational potential and also gravitational potential energy. Right? So how do we understand in detail the electrical potential and also the potential energy? So first of all, where it comes from? Where does this potential or the energy of electricity come from? Let's look at this kind of scenario. You have a point charge Q naught. At the same time, you have an electrical field E. You have an electrical field E, right? So if we assume this to be positive, then there will be an electrical force also pointing this direction. Right? This is the E, this is the F. Right? And for this charge Q naught under this electrical force, F pointing to the left, what will happen to this charge? Of course, it will move from this point to this point to another point. Right? Let's say from A to B. So this is what will happen for a charge under an electrical force. And if we look at this process, first of all, we say there is a force, there is a work done by the electrical force. And this work is quantified by this. This is the force. The force times the displacement is the work done by a force, right? Basically, the general formula is this, right? The work done by a force equals to the force times the displacement. Now it's just the force is an electrical force, and for electrical force, E equals to this Q times E, right, in terms of electrical field. Right? And still, you will have this displacement. And this is the work done by the electrical force. And once there is a work done by the electrical force, we say there is a change in electrical potential energy. And this one is written in terms of the dU. And the change of the electrical potential energy should just equal to the work done by the electrical force. And of course, there is a minus sign, means positive work will reduce the electrical potential energy. Right. And once we have this relation between the work and potential energy, then we can do the same discussion basically for two specific points. Let's say from point A to point B, we can tell there will be a potential energy difference, UAB, and it just should equals to this, right? The integration of dU from point A to point B. The dU is just the potential energy difference due to a tiny displacement ds. Now, for a finite displacement from A to B, then it should equals to this integration from A to B, right? And again, this du equals to this. So you can see this is a dw, and du is minus dw, so you can tell this is the UAB, the potential energy difference between point A and point B. And of course, generally, if we can define the electrical potential energy of point A and point B, then very straightforwardly we can tell the potential energy difference should just equal this UB minus UA. If this UB is the potential energy at point B and UA is the potential energy at point A, right? So here, basically now we build up the connection between E and U. E is a parameter we have been discussing so far, and U is a new parameter we are going to discuss in more detail. So you see the connection from what we already discussed to the new parameter that we are going to introduce. And once we have this electrical potential energy, U, we can further define another parameter, the so-called electrical potential, V, in this way. So basically, the electrical potential V is the potential energy per unit charge, Right, so now again, from U to V. Step by step, how we can introduce new parameters and also the relation with the existing parameters. So this, and of course, we can also do this differentiation to find out this dV in terms of dQ. Basically, the potential difference dV or potential energy difference du for infinite small displacement ds. For infinite small displacement ds. Right? So again, you can see now basically we can have this relation from E to V, E to V. And again, if we are interested in the potential at a specific point, let's say point A or point B, then we can define this VBVA. VBVA. And we have UB to VB, UA to VA. Right? It's all one-to-one relation. So here all those are actually it's just the same formula of different version. The important one, this one, the formula 1 and the formula 2. With these two, then immediately, or at least after some practice, immediately you can write down all those additional different versions, like this one, this one, this one. Right? So you don't need to memorize. You don't need to memorize. All you need to do is do some practice so you get at least be familiar with them. Right. So, okay, this is pretty much the two new parameters and also the involved new formula we are going to discuss for the electrical potential and electrical potential energy. Right? And the following slides is just how we can understand the electricity from the perspective of electrical potential and electrical potential energy. And the first one, is the so-called equal potential surface. And here, the equal potential surface just means any surface, any 2 points on the surface, the electrical potential is the same. So the meaning is very straightforward, equal potential surface. Any 2 points on the surface, the potential is the same, V is the same. Right? Let's say if this one, this kind of arbitrarily equal potential surface, meaning at this point, this point, this point, this point, V1, V2, V3, V4, all the same. All the same. And if V are all the same, of course, then we can tell delta V. Let's say from V1 minus V2, V2 minus V3, all the delta V should be 0. And if delta V is 0, the delta U, the potential energy difference, is always 0 for any 2 points on the equal potential surface. Right? Meaning if you're moving from a charge, if you are moving a charge, let's say from this point to this point, or from this point to this point, although the path, the geometric path may be different, but the work you need to do is always 0. It's the same and always to be 0. Simply because this one, right, delta U must be 0. This is the first understanding or the first property of equal potential surface. And the second property is if we say this delta V is always 0, then we already know here the relation between V, AB, and electrical field E. If this VAB is always 0, means this dot product is always 0, right? And how can you make sure the dot product is always 0? Cosine 90 degree. E and ds always perpendicular, right? So, of course, along the surface, this is going to be the ds. And if E is perpendicular to this, then means this way, right? Or another way to say, for an equal potential surface, at any point, the electrical field E is always along the surface normal. Always along the surface normal. Only in this condition, this E dot A is always 0. Theta V is always 0. Right. So this is the electrical potential and also equal potential surface. So now we establish this new concept and also some basic formula, some general formula. Now next, what we are going to do is to try to determine the electrical potential and potential energy for a single point charge. It's just like what we did for the electrical field E. First, we introduce the concept, introduce the concept, and also give you the basic formula, the general formula. Then we try to quantify this parameter for the most basic scenario, that is point charge or single point charge, right? So now we are doing this for this V and U, potential energy. Okay. So first of all, we can tell, of course, we already have this one, E due to point charge Q, right? Now we need to derive V from E. And from E to V, this is the formula. From E to V, right? And if we are talking about two specific points, basically you need to do this integration of the dot product from A to B. And E, this is the E. This is the E. And this is the ds, right? So now, in the following step, there's going to be some geometric or mathematical conversion and also some integration, right? Here, of course, we can tell, let's say if we look at this particular point, the vector R, this vector R basically is a direction of E. It should be along this direction because this is due to point charge. Let's assume to be positive. Right, so this is going to be the this vector R, right? And the ds is just a displacement from A to B. So it should be pointing this direction. There is going to be a finite angle, let's say theta, between the vector R and ds. That is cosine theta. So that is why you can basically, why this one equals this one. The dot product of these two vectors equals to this ds cosine theta, right? And again, here you can see, of course, this Ke are constant, Q is also fixed constant. What you need to do, if you do this in terms of this dr, then what you need is just the integration of this part. integration of this part, dr over r squared. And of course, here you will need to know the integration of dr over r squared is just this 1 over r. It's just this is something you should know from the calculus. And from here, what we determine is the potential difference VAB, right? If we want to figure out the potential at a specific point, let's say this point B. If we want to figure out this VB, basically we need to make this VA to be 0, right? If VA is 0, then the potential difference is just the VB, right? So how we can make this VA to be 0? You make this VR, this RA to be infinite large, So that is why this VB is just E equals to this. And this is the potential difference due to a single point charge Q at the point with a distance of RB, right? And of course, we can generalize this to be any value of R. So V equals to this KQ over R. And this is valid similarly for only when this Q is a point charge. Only when this Q is a point charge. And this is the case for a single point charge. If you have multiple point charge, so you see the so-called principle of superposition. You just find out this V1 plus V2 plus V3. That is going to be the total V. And the difference is now here, this potential is not a vector. It's just a scalar. Means you only need to consider its magnitude. There is no direction for V. That is why here it's just not a vector sum. Where for this E, we know for this E, similar, if you are using the similar principle of superposition, you need to find out the vector sum, right? So this is the difference. So, and similarly, if we want to find out this potential energy for point charge, this is the formula. So you can see basically this one gives you the potential energy U due to 2 point charge Q1 and Q2 with a distance of R12. So how this is derived? Let's say we consider this kind of two-charge system, Q1, Q2. Initially, we can just put these two charges to be, both of them to be infinite far away. If they are infinite far away, we just can consider the potential energy or the electrical potential energy between them should be 0, right? Now, if we move this two charge initially infinite far away to certain location with a distance of R12, this process, let's say initially you have this A somewhere here, B somewhere here, considered to be infinite far away, right? And at this state, the potential energy, of course, is 0. So what you are doing now, step 1, you're moving this charge A from this point to this point, right? And this process, still, there should be no potential energy difference because here, infinite far away, V is 0. V is 0. And initially, before you moving any of them, initially in this space, V is also 0, right? Because you don't have any point charge, right? So if you don't have any point charge, Q is 0, V is 0, right? So means if you move this charge A from one 0 potential point to another 0 potential point, you don't need to do any work. Delta V is 0, so delta U is also 0, right? This is step 1. Step 1. Now, once you have this charge Q1 at this point A, basically you will have a finite, you will have this, at this space, you will have a finite V due to this charge at point A, which equals to KQ1 over R, right? Because now you already have a single point charge, so in the space there will be an electrical potential, right? So meaning, once you have this charge here, then at this point, this VB is not going to be 0, right? So it's not going to be 0. It's going to be a finite potential. So at this point, you do this. Move the second charge from infinite far away to this point. So there will be a delta V and also delta U, right? And this delta V is just the KQ1 over R12. That is this one. This is the delta V. This is the delta V from here to here, right? And delta V times the Q, that is delta U, right? So you can see delta V times Q is delta U, the change of the electrical potential energy. And eventually, here another Q2. Eventually, you get this one. So this is how you get this total potential energy U equals this KQ1, Q2 over R12. And of course, based on what we just described, the physical meaning of this U basically it's the energy or the work you need to do in order to assemble this kind of charge system from infinite far away to a finite distance. The work you need to do to complete this process, that is U. And this is the two charge system. If you have multiple charge system, then the total potential energy, basically you need to consider each pair. Like if you have three charge, then you need to consider the potential energy between Q1, Q2. You also need to consider the potential energy between Q1, Q3. Also the potential energy between Q2, Q3. Right? Each pair of charge will give you a potential energy. So this is the case for three charge. Of course, let's say if you have another Q4, then how many terms will you have? For three charge, you have three components. So how about four charge? How many? 5. So what are the additional 2? 3, 4. 2, 4. So that is how many? 6. Yes. If you have 4 charge, then basically you have 6 pair of point charge, and each pair will contribute a finite potential energy. And similarly, here is still finite number of point charge. If we want to determine this V and U for this kind of continuous charge distribution, again you can see we have done this for E, right? We have done this for E. Electrical field E due to the continuous charge distribution. Now we will do this for V and U. And similar idea for this V. We have this one to be valid only for single point charge. And now if this entire charge is not a single point charge, what we can do is to create this dq1, dq2, dq3 all the way, and we do the integration. And this should give you the total V. Again, you see exactly the same idea we did for E, electrical field E, right? So it's just now the formula is a bit different. Now here is KQ over R, while for the E, it's KQ over R squared. Right? This is one way we can determine the electrical potential V. Another way, if we can somehow, first of all, determine the electrical field E, then we also have this formula, again, from E to V, right? And what is the most common way we can determine electrical field E? That is the Gauss's law, right? As we just mentioned, the most common, most typical application of Gauss's law is to determine electrical field E. And if you do that, you determine the E first, and then move on with this one. You can also determine the electrical potential V. Okay, so we can, before we discuss this example, any questions? Again, try to do this one-to-one comparison between E and V. Right? So then it becomes more clear. Okay, so if no question, let's look at this example. So ask you to determine the electrical potential V at the point P located on the perpendicular central X of a uniformly charged ring. And the total charge carried by this Q, by this ring, is capital Q. So again, we have generally we have this method 1, method 2 to determine the V, right? So in this case, how are we going to do it? Which one is more likely to be feasible? From this method 1 or method 2? If you want to use this method 2, basically you need to consider, can you somehow determine E first, right? And in this case, actually we can just use this method 1, starting from the single point charge. a single point. Of course, overall, the entire ring cannot be considered as a single point charge. And if this is the case, what we need to do is to create this kind of tiny portion, and the charge carried by this tiny portion, dq, can be considered as a single point charge. Once we have this single point charge, we can have this dv, basically dv due to this dq, which is ke times dq over r. Right? This is step 1. And then step 2, if we do this integration of this dv over the entire charge object, which in this case is a ring. So you do this integration over the entire ring. By right, what you get should be the total potential, right? So then if we can move on. Here is dq, and this r, in this case, this is r. This is r, right? So it's square root of x squared plus a squared. And you can see all these x, a are constant in this case. In this case, x is also a constant. So all you need to do is to do this integration of dq over the entire ring. And the physical meaning of this is just the total charge carried by this ring. And that is the capital Q. Right? So you can find out this V, electrical potential, due to this kind of charge object. Okay, so next is again some kind of understanding, or you can also say basic property of conductors in terms of electrical potential. Just now we say for a conductor under the electrostatic equilibrium condition, Q in is always 0, and electrical field E inside is always 0. So how about electrical potential? Is there any similar conclusion we can derive? Right. So let's look at this kind of conductor. This kind of conductor, we know, again, Q in is 0. Inside the conductor, Q is 0. E is also 0. Right? And how about the electrical potential? First of all, let's look at the 2 points, point A and point B. Both of them are on the conductor surface. Both of them are on the conductor surface. Then we can tell the potential difference VAB should equal to this, right? The integration of this dot product. Integration of this dot product. And we already know for this kind of surface, at any point, E is along surface normal. The direction of E is always along surface normal, meaning this dot product is always 0, right? And this VAB is always 0 as long as these 2 points A and B, both of them are on the surface. Means any 2 points on the surface, the potential is the same. The potential difference is 0, then the potential is the same. So that is to say, based on this analysis, we can determine that for the entire conductor surface, it is an equal potential surface, right? It is an equal potential surface. This is the same, the first point. And how about inside the conductor? So if we look at a point C inside the conductor, C is inside the conductor. And if we try to derive the potential difference between C and B, then it's going to be like this, right? Or similarly, do the integration from C to B. If we do this integration from C to B, what's the result? The integration of EDS from C to B. C is inside, B is on the surface. Let's say along this way. It should be how much? C is inside the conductor. B is on the conductor surface. So basically, from this point to this point. And you can see the trajectory inside basically is all inside the conductor, right? And inside conductor, we have this, right? Means E is always 0. E is always 0, then of course this dot product is always going to be 0. That is to say, the VCB is also equals 0. VCB is 0, means VC always equals VB and always equals VA. Right? Means the entire conductor, any 2 points, inside or on the surface, any 2 points, the potential is the same. The potential is the same. Right? So the potential V is constant everywhere in the conductor. Right? So this is another very important understanding. I would say you should immediately immediately come into your mind when you try to solve certain questions. So basically, 1, 2, 3, or delta V is always 0. These are the 3 very important properties for a conductor. Inside, Q and E are 0, and one more, the entire conductor is an equal potential object. So here, any questions? You do understand why VA equals VB and also equals VC. Any questions? No. Okay, so I guess we have one more example. Here is a solid spherical conductor, radius of this capital R, also having a total charge capital Q, and it is uniformly distributed on the surface. Ask you to determine the potential an electrical field, basically V and E. Also inside, outside the conductor. Right? So here, what we need to do, actually, if you recall, we already have this one. We already derived this based on the Gauss's law. Inside the conductor, E is 0, and then outside the conductor, E is decay in this way. We already derived this based on the Gauss's law, right? And that is to say, we already have the electrical field E. And from E to V, we can use this one. Right? So this is exactly the same procedure we have done, right, to determine the electrical field E using the Gauss's law. And once we have this, we can continue from E again to V. Of course, here in order to determine the V at a particular point, normally we need to do this integration start from infinite far away, because at this point we always consider V to be 0. This is something you can take for granted, meaning the electrical potential at infinite far away is always 0. Right? So that is why here you have this kind of integration. Eventually, to find out this is the electrical potential. So you can see if you try to plot this electrical potential as a function of distance. This is inside the conductor. It's a constant, a finite constant value. And outside the conductor is decay as a function of 1 over r. While for this electrical field E, inside is 0. Inside is 0. Then outside the conductor, it decays as a function of 1 over r squared. 1 over r squared here. Right. So this is an example. So because we already go through the detailed analysis of how we use the Gauss's law to determine E, then here it becomes quite straightforward for the additional step from E to V. Okay, I guess this is pretty much all we need to cover for the electrical field and also the electrical potential, of course, the potential energy. Right. So if no more questions, then that is all for today. So I will see you tomorrow for the quiz and also for the tutorial.